Sequencing methods we are going to talk about. So far, most of the design relying on the flip-flop. So typical flip-flop sequencing has the flip-flop at the input and flip-flop at the output. First, the flip-flop launch the data at the rising edge, right here, and then after certain delay through the combination logic, in the next clock edge, we will catch the output of the evaluation value from the combination logic. So for the clock period TC, where data ripple through the combination logic, and we get this, the output at the finally, just before next clock rising edge happen. We may use two-phase latches, so first latch like that, and second latch phase like that. So make sure that we have a non-overlap, so overlapping doesn't happen in this example. So for first latch, while it is transparent, the data comes in and then propagate through the combination logic, and then next feed 2 enabled. Until that is enabled, the feed 2, the data arrives here and wait for the feed 2 to go up. And then once the feed 2 goes up, the data again launched onto the second latch output, and then pass through, ripple through the combination logic and wait for another V1 until the wait for the V1 to go up. We can narrow down this latch operation and using one latch in one phases, that is pulse latch, very narrow pulse width of the latching clock signal, so that only we catch the data when the clock pulse is high. So we have to make sure that input data onto the latch for this kind of a pulse latch must be stable, so that the output, when this latch clock is high, the input data should not changes. Once that data is properly captured onto the latch, then data comes out from the latch and propagates through the combination logic. This pulse latch and flip-flop are similar operation, but it requires some, for the flip-flop, event beginning of the event and the end of the event will be defined by the clock edge here. But for the pulse latch is that it just specified beginning and end is specified by the pulse, right? All those three elements, so the time for the combination logic to complete each operation is spared for about 1 clock cycle, right? But for the two-phase latches, we have the non-overlap period. That kind of a period is kind of waste. We cannot use that period for logic calculation, right? That is a waste. That's the penalty. That's why the people thought of this pulse latch. In this pulse latch, only the pulse width is kind of waste. This cannot be used for the logic operation. So it's a little different. This is advanced from the two-phase latches. For timing diagram, the combination logic and flip-flop and latch, it involves some data transition and output transition timing. This is very important for you to understand and what would be the potential issue. For typical combination logic, we know that for the input changes, some of the output will come out early and some of the output will come out late. So we have a minimum and maximum delay through the combination logic. So minimum delay, we call it contamination delay, TC, logic contamination delay. and maximum delay, logic propagation delay. So the max delay, the minimum delay. For the flip-flop, each action happen when the edge from the clock edge. We know that from the clock to Q delay, so Q propagation delay, sometimes rising edge to Q delay is shorter. The CCT contamination, because of the contamination delay, the clock output changes happen. TCCQ, it's not here. Latch flip-flop contamination delay and TPCQ, latch flip-flop propagation delay. This is max and min again. Why we have this kind of a maximum minimum delay? Sometimes if the data coming into this kind of rising edge of the clock, if the data changes is too early to the clock rising edge, it will take more time to resolve whether that is 1 or 0, depending on. So this kind of a data timing affect the clock to Q delay, so it can be sometimes faster or sometimes slower. And also there's a hold time. The hold time definition is there. So in order for the flip-flop to work properly, the data should not change until some certain period even after the clock rising edge happen. The input need to stay high. That's called the hold time. The hold time clock, we have a latch flip-flop hold time even with the some data clock event happen. The input should not change. For the latch, the hold time is defined similarly. Actual event, critical event happen when the clock edge goes down. Clock goes down. At that time, we hold the value. So, in order for holding operation to be properly done, so there should be input data should not changes until the hold completes. Right? This is the hold time. This kind of a latch, kind of very complicated, right? We have when the data comes in, we have output, so we have a minimum delay and maximum delay here, right? During and also input data should not change when the clock edge goes down. This kind of a minimum time for. So data should not change before the clock edge happen. This is called T setup time. The similarly flip-flop also define the setup time. So the data should not change before certain period. That means the setup time, right? Setup should be guaranteed in order for that for the flip-flop to work. We have a setup and hold. So for the flip-flop, we have the rising edge here. From the left-hand side, we define setup time, and right-hand side, we define hold time, right? So there's a certain window defined by we have a clock edge. There's a certain window by the T setup and T hold. In this window, data should not change, right? That's kind of important requirement for the flip-flop operation. And also latch also, there's a certain window that requires data should not change. That window defined when the clock goes down here, because this is level sensitive. Hold mode operation start operating when the clock goes down. So there's just one certain window there, again defined by setup and hold. The data should not change. As you can see, the flip-flop timing versus the latching timing, you can see that the latching time is a very complicated, more complicated structure there. But what we need is similarly defined, right? Shown in this table. So what would be the maximum delay we can allow for the combination logic? We know that for the flip-flop there is a clock to Q delay, certain clock to Q delay. Starting from here, the logic start combination logic to take the input and start operating. It will come out the output at certain delay TPD, and then we know that there's a certain requirement for the flip-flop, for the receiving flip-flop. We require the setup time. For during that setup time, the data should not changes. So you can equate the equation. So what would be the maximum propagation delay allowed for the flip-flop? So overall, 1 TC equal should be TPCQ plus a TPD plus a T setup, right? This is critical limit. If you so TC must be greater than equal to hold the sum of those timing data. So this equation will lead to the final inequality equation there. So smaller the setup time, smaller the setup time, and smaller the clock to Q delay, you will get more time for the logic operation. Okay. So this is the sequencing overhead. Right, smaller those value will lead us the longer time for the combination logic. Now let's calculate the latch delay, the maximum delay for the two-phase latches. We have a latches and 1 and 2 and 3, and each between latches we have a combinational logic. When the data comes in, first it passes through the latch delay, and then first combination logic delay, and then latch 2 delay, and another combination logic delay. Then must comes in, and the whole thing must be within the TC 1 clock period. So TPQ1 plus TPD1 plus that equal to delay plus TPDQ2 TPDQ2 plus TPD2, right? So that gives us here TPDQ1 plus a TPDQ2. So this is the sequencing overhead that comes from the latch delay. So if we assume that this TPDQ1 and TPDQ2 are equal, we can write down 2 TPDQ. This is the sequencing overhead. One thing to note is that so we can make it so the propagation delay, the sum of the propagation delay must be less than this number. So TPD1 can be a little bit larger, like in this figure, passing through this a little bit larger. Even it doesn't have to be completed before half clock cycle. It just can over the half clock cycle, then it can complete and then continue the operation. So in this way we can we call it like a time borrowing. We borrow the time for combination logic operation from the combination logic 2 passes, right? So we can allow or allocate the completion time, the logic combination logic time for one more slightly greater than the combination logic 2. But the sum of those two combination logic delay must be less than this approximately 1 clock cycle. For the post delay, we can also write down between the latches. We have combination logic. So starting from the input data, so we have the sum of all these must be greater than must be less than 1 clock period. So TPDQ, this is latch delay plus propagation delay, that must be less than clock cycle, right? This is one cases. So when the data comes in and directly during for the post latches, there's another data, the timing path. So previously we just calculated from D1 to the D1 to phi, but the other clock path is phi1 to phi, the latchy, go to latchy. So there are two passes. The first pass we calculated from the data, the latch propagation delay plus the combination logic must be less than 1 clock period. The second case is when the clock phi goes up, the clock to Q delay will happen now, and the propagation delay, and then it can pass this rising edge, because even after this rising edge, because of the latch, we can still catch the value until the falling edge happen here. So we have even more margin of the TPW. It's similar to this is a similar concept of the time borrowing. So TC plus TPW, that should be greater than TPCQ plus TPD, right? And plus there's a setup time for this falling edge, so T setup. So one requirement like this, from this data path, we have additional requirement like that. So TPD Q, D to Q delay plus TPD, right? So we have a two equation, that two cases that must satisfy. So we choose between those two the propagation delay, the minimum propagation delay, or the worst case propagation delay should be set by this maximum of those two cases. So TPD, we can find that in the next slide. We move that to here. Here, this portion move to the left, and where is it? This and this move to the left, like that. So finally, we have this condition for the worst case delay of the propagation logic, and the pulse latch we can calculate like this. This is the maximum between those two. The maximum will subtract it from the TC. That will give us the worst case propagation delay condition. Now we also need to check out the minimum delay requirement on the flip-flop systems. As I explained before, the input data should stay hold even after rising edge happen. So that is defined by the T hold. So T hold there. So that should be the D2 be stay satisfied there. So first the data launched from the F1 will start from the rising edge of the clock that will go through the contamination delay of the clock to Q delay. So CQ, this is contamination delay, the faster delay, and also it goes through the contamination delay through the combination logic, that is the faster delay, T plus TCD. That must be greater than hold time period. So minimum contamination delay through the combination logic should be defined by a T hold minus T clock to Q contamination delay, TCCQ. This is the minimum, the faster delay requirement for the combination logic. So you have to check it out. For checking out this minimum delay, you have to be very careful about that there's two flip-flops in here, right? The whole time check we are doing on the F2. So data comes out, the timing coming in or staying hold should be specified by this T hold, right? That T hold from clock to combination logic to D2. This kind of a path delay must be longer than the whole time requirement, right? So that specifies the minimum amount of the combination logic delay TCD that is defined by contamination delay. In the two-phase latches, we can calculate the earliest time from the phi1 to D2. That is calculated from when the clock phi1 goes up, the data comes out through the T CCQ, contamination delay of the clock to Q delay, plus contamination delay of the logic delay CL. That's the earliest time that we have, and also we have a non-overlapping, and there is a certain hold time delay specified from the falling edge of the phi2 on the L2 latches. That should be T hold. So there's a non-overlapping time between phi1 and phi2, so T non-overlap plus hold these thing must be longer than the whole time, so that the data on the L2 will stay high enough, right? There is certain there's a whole time requirement. Data should stay high even after this falling clock phi2 falling edge happen. There should be, the data should hold. This is a requirement of the T hold. So we can rewrite this TCD in terms of CCD should be T hold minus T non-overlap plus TCCQ, right? This holds for both latch 1 and latch 2. Right? This is something that we have. From this equation, we can see that if we have a larger non-overlapping time, then the minimum contamination delay getting larger. So the whole time violation is kind of the actual hold time is reduced by this non-overlapping period, the larger non-overlapping. So this is good for meeting whole time violation, right? So we are having more, we can put more delay, we can make it shorter delay on the the logic path by having holes on the right term will become smaller for the large non-overlapping, right? So actually this relaxes the meeting the whole time violation by having large non-overlapping period. For the post latch, the minimum path delay we can calculate from when the phi clock goes up. For the pulse, we can start from this example. At the time of the phi goes up, data comes out through the flip-flop. So T's clock to Q contains the fast clock to Q delay plus the minimum delay through the combination logic, that is the contamination delay. That one should be greater than equal the hold time requirement. Hold time specified from the folding edge of the latch. So for the same starting point, we have to add pulse width plus T hold, right? So finally, the TCD contamination delay will be calculated by TPW pulse width plus T hold minus T clock to Q delay. The fast case is the clock to Q delay, right? So by having this equation there, we can see that hold time requirement is increased by the pulse width. So hold time is increased. So if we have a larger pulse width, the minimum delay is become larger. So we need certain more delay on the combination logic there, right? So this kind of larger the pulse width, it is difficult to meet the whole time, right? Because it's larger delay, minimum delay, so minimum delay become larger for the combination logic. So this is the actual equation that we have written. We can double check. In a typical flip-flop system, you have a flip-flop at the here, the combination logic and receiving flip-flop there. So data launched on the rising edge of the clock here, CLK comes in, rising edge of the clock, and then the input to the flip-flop must settle before some time, right? So that is defined by the setup time. So input data must set up before the next rising edge. So if that data comes later than the rising edge, then it fails. This is very important. But if it arrived too early, then the time is wasted. For example, when the clock comes in and then D0 and D1 there, D0 comes out and D1 comes out through some combination logic delay, TCL there. Up until from this point to the next rising edge, there's no activity here. We can do some more logic operation, but we are wasting the time. So time is wasted if the data arrive too early. So the flip-flop has very hard edges, meaning it has definitely the fixed edges that operate. So it always, for the rising edge flip-flop, it operates only at the rising edge of the clock. But in the latch system, it doesn't have hard edges. It can pass through the latch while it is transparent. So the long cycle of the logic can borrow time into the next. This is the concept of time borrowing. But there's a restriction there. Each loop must complete one cycle. So for the latch operation, you have the latch here. It's a latch here, combination logic, latch here, combination logic, latch here. This is the phi, this is the phi bar and phi, right? If you start from phi to phi bar, it seems like the master and slave latch. It is like a flip-flop. So some of those CL1 and CL2 must complete within one cycle, but between those two, we can borrow the timing from one from the other, right? Inside the flip-flop is master latch and slave latch there. We are moving the slave latch in the middle of the combination logic in a flip-flop system. So configurations becomes similar like that. So phi latch, first latch gets the phi, and second latch get the phi bar latch, the inverted version, right? So this is very similar to the flip-flop system, but we are moving the second latch, slave latch, into the combination logic. By doing this, we can borrow some time from the adjacent clock phases. This is an example of time borrowing. In the latch system, we have a phi1 and phi2 in clock inversion relationship. We have the logic there. Even though the first combination logic passed through this falling edge of the phi1 falling edge, it can continue to operate, and because the phi2, while it is phi2 there, the data comes late, can still pass through the latch, second latch, and continue each operation, right? This is different from flip-flop based, right? Flip-flop based has a hard time event, rising edge, for example. If we miss the next rising edge, you cannot pass through the flip-flop. But in the latch, it has a transparent mode, so it can still pass through the latch during the transparent mode, right? So this is called the time borrowing. But if there is a loop inside the time borrowing, then this loop must complete within one cycle. You can think of this as the flip-flop. You put this phi1 and phi2 put together, then it becomes a flip-flop, right? Flip-flop system, it must complete each cycle within one cycle, right? Even though you get the time borrowing must complete within the cycle, right? If there is the feedback there. If there is no feedback, you can keep borrowing across the clock. You can still borrow the time across the pipeline stage boundary, right? This is a different feature of using the latch system. So this is a very complicated timing check. For most of the CAD tool cannot handle this kind of a latch-based system because it is too complicated. Timing check is difficult. So most of the time we avoid to use this kind of latch-based system. Let's calculate how much actually time borrowing can happen. We define the time borrowing from the second phase of starting from the second phase of the rising edge of the second phase. From that, this is time borrowing. That means that the combination logic still can operate, right? Even after passing this second phase V2. This is the half cycle and time borrowing. So what's the relationship there? We have the 1 clock cycle here, starting from the V1. Half cycle plus T borrow. This is something how we calculate. So launched from wait a second. So this is time borrowing starting from here. After time borrowing, we need some setup time required, right? Until the falling edge happens. So T borrow plus T setup, right? Plus non-overlap, right? Plus T non-overlap must within complete below the half cycle, right? Equal to. So this gives us this relationship, right? A similar calculation can be done for pulse latch. Pulse latch can borrow time just small amount, like a T pulse width minus T setup. But in two-phase latches, we can borrow a lot of the time, almost half cycle minus normal overlap and T setup. So almost half cycle, we can borrow the time. Because the two-phase latch, we get most of the time the transparent mode is very long, but post latch mode the transparent time is very short, right? So we get the very short time borrowing there. So far we just assume that there's no clock skew, so all the flip-flop here between logic, combination logic we have in between. The clock 1 and clock 2 arrives at the same time. But in reality, there's RC delay difference from the metal line, right? So there's some skew there. Or if you have a lot of the flip-flop there, we have to add some buffer there. So buffer delay may lead to the clock skew on clock. So clocks really have the uncertainty in arrival time. So this actually sometimes it may decrease the maximum propagation delay of the combination logic, or sometimes it increases the minimum contamination delay. What would happen? So for the first case, under what condition the maximum propagation delay will decrease? If the clock arrives faster, so CK1 is like this, and CK2 arrives faster, right? For example, CK2. Then the operation for the combination logic is limited on this reduced clock phase, right? That actually reduced the maximum propagation delay. What about the minimum contamination delay? In case, how we can increase the contamination delay? If the clock phase 1 is slower on this. For this example, the minimum contamination, the minimum faster delay, allow the faster delay of the combination logic if the clock phase comes early, CK1, the CK2, like that. From this arrangement, you can have a chance of data just latched on the just next to clock 2 rising edge. We wanted to catch the data, the data launched from the clock 1. We want that to be catched on the next rising edge, but by having clock skew, it will catch just at the same time, the clock edge at the same time will catch the data. This will make a false operation. So you require more contamination delay, more delay from clock 1 to data out. This require more contamination delay on the clock combination logic, right? In latches system, it may reduce the time borrowing. So clock skew is very critical and important to make it small. Let's take a look at in more detail. In flip-flop system, we have a clock here. Clock has a variation like this. Let's say data launched on the F1 flip-flop, launched on the clock rising edge and passed through clock to Q delay and propagation delay and setup. Because of the clock skew, if there is the clock 2 on the F2, if it arrives earlier, like this shown in here, by the clock skew, then you actually get the smaller, the combination logic delay is required. So we can add the equation for propagation delay is clock to Q delay setup time plus T skew. So actually reduced this amount of time for allowed for combination logic is reduced by that clock skew. For contamination delay, calculation is shown here also. So if there is a clock skew there, if the data, the hold time required for this F2 is T hold, but if the clock on the F1 is launched earlier like that, then we need more contamination delay from the CL. So we need more delay, minimum delay of the CL to satisfy the hold time, right? This is the equation that we must follow. In two-phase latches, the effect of the skew can be calculated here. In this example, so we have the combination logic. Maximum propagation delay is not sensitive to the skew because of the time borrowing. So time borrowing actually doesn't have impact on the propagation delay of the combination logic. But for the contamination delay, the clock skew, the worst case, the clock skew will impact on the contamination delay. Also, time borrowing, amount of time borrowing is also affected. For post-phase, post-latch system, the maximum propagation delay is affected by like that, and then also contamination delay and amount of time borrowing also reduced. So I'm not gonna go over the detailed calculation, but as you can see, the clock skew is very critical in most of the clocking system in sequencing the elements. So we must avoid the clock skew and try to make our timing margin and considering the clock skew. In two-phase clocking system, if the setup time is violated, so the combination logic has longer path delay, so we can reduce the clock speed to make it work. But if the hold time is violated, the minimum delay is violated, chip fail at any speed. Even though you reduce the clock speed, the chip will fail because the minimum path delay doesn't change even if you change the clock speed. So analyzing the skew and hold time violation thing is very, very important to make it work. So easy way to guarantee hold time violation, fix the hold time or guarantee the hold time is to use two-phase latches with big overlaps, right? The amount of the overlap period will add more the margin on the hold time checking, but it has a kind of limitation. We need to have two clock phases, two clock tree or clock buffer must be implemented, and the timing check is not easily checked on the typical CAD tool. So if we use a V1 and V2 like a two-phase system, the two-phase is the most easy way to guarantee the hold time. This is the advantage of the two-phase clocking system. If we have the flip-flop with non-inverting clock, like to ensure that no clock skew effect, so to handle, the hold time violation, if you can use non-overlapping clock for V1 and V2 even in the flip-flop, but it becomes more slow, so it adds more setup time. It requires more setup time, but you can avoid that the data just pass through this the flip-flop, right? This is called race condition. The race condition is avoided by two-phase non-overlapping clock. But because of this the timing burden or the hardware complexity, most of the industry we use better timing analyzer, meaning the CAD tool will handle this kind of the skew, hold time and setup time risk. Typically, CAD tool add more buffer to increase the minimum delay of the combination logic, so make it slower if that is too fast. So hold time is guaranteed. This is the summary of this chapter. The flip-flop based system is very easy to use and supported by all the tools. So this is a very golden standard that we are relying on, or we are designing based on that. And two-phase transparent latch, you can have a lot of skew tolerance and also has time borrowing, but most of the CAD tool cannot easily handle that timing because the timing check is very complicated. And pulsed latch can work similarly to flip-flop based system, also the transparent two-phase latches by having more borrowing capability, but it has just some hold time risk, and also some tool cannot the tool cannot easily handle this. It can be fast because of the single latch based versus the two latch master slave latch required in the flip-flop based system, but in pulse latch it only requires one latch, but the pulse width need to be very small, narrow. So this kind of a narrow pulse width cannot be easily distributed across the clock tree because the finite rise and fall time through the inverter. So if you have a pulse width like that, the inverter output will have like a diminishing pulse width. Even after several buffer stages, the clock pulse may disappear. So it is very difficult to maintain such clock, narrow pulse clock throughout the whole chip. So these are the equation that we have developed in this lecture. You can go through and see some difference, right? As you can see, the most easy, simple equation comes from, right, flip-flop based, right? This is the most golden method that people are using for digital design.